Hello, everyone. Welcome to lecture 13 of AREC 333. Today, we will continue with the economic aspect of production for two-input case. The plan for today is to first finish our example of the extension path for Cobb-Douglas function. And after that, we will explain the duality relationship between cost minimization and output maximization. I will, when we get there, I will explain what the duality means. And when we're finished with both of that, then we will actually do the profit maximization from input perspective for two or more inputs. Here, I also put one last bullet point, factor demand functions. That's what's gonna come after today's lecture, so maybe for next lecture. And if you are interested, you can spend some time on the suggested readings. So here, chapter 13 of the burden is actually about input demand functions, or factor demand function. It's the same thing. So if you are interested, you can read that chapter, and all of the rest of the readings are relevant for today's lecture. This is the cost minimization example that we used in last lecture. We assumed that the production function is a Cobb-Douglas function, and here we have the parameters beta 1 and beta 2. One is 1/3, and the other is 2/3. And I did show you how to solve that cost minimization problem. And when we solve a cost minimization problem, what we did is that we found a solution to one particular isoquant. So for this given output level, then we find out the point where the combination of inputs, the cost of that combination is the lowest. And if we remember, the definition of expansion path is actually a path or a curve which connects all of the least cost combinations for all levels of output. So previously, in the previous slide, what we solved is just for one isoquant or one output level. So how are we gonna find out the expansion path? And if you're not having a Cobb-Douglas function, or if you're not having a homogeneous function, or even more generally a homostatic function, but homostatic function is not covered in this course. So let's say if you have a quadratic production function for two inputs, which is not homogeneous, then in order to find the expansion path, you actually have to solve the cost minimization problem for each level of y. So you have to solve a bunch of different optimization problem. However, for Cobb-Douglas function, there is a nice property about the expansion path. But before that, we need to go back to our lecture 11, where we mentioned there is a nice property of homogeneous functions, which is that the RTS, rate of technical substitution, along a ray line is constant. So RTS, if you do remember, is the ratio of the MPPs, and which is also the slope of your isoquant curves. So here, this is the slope of the isoquant at that point. And if you're changing your input along this line, that means for each isoquant curve, then the rate of technical substitution is gonna be exactly the same. And why is that important? And this is actually related to the optimization condition that we have explained in last lecture. So the implication of a constant RTS is that the slope of the isoquant curves is the same along any particular ray line. So this is one ray line. This is another ray line. There could be other ray lines. Along each of those ray lines, the RTS is going to be the same. And if you do remember the solution to the cost minimization problem, or if you want to find the least cost combination of inputs, then the solution has to satisfy this condition where the ratio of the inputs are equal to the ratio of the two MPPs. So we know this part is constant along ray lines, and we also know if we were given particular input prices for both input 1 and input 2, then the ratio of R1 over R2 is also constant. So what does that mean is if you're moving along this ray line, then the R1 over R2, the price ratio of that two inputs is constant, and the ratio of the MPPs is constant. So that means your solution doesn't change if you're moving from this point to that point. So as long as you stay on that ray line. That means if you find one solution to your cost minimization problem, so for one isoquant, or you can also say for one particular output level, then the solution is the same. All you need to do is that you connect from here. Let me show you this. So if, for example, we find the solution there, that's for this isoquant, that's the least cost combination for that output level. Then you want to know along this isoquant curve what is the least cost combination. You don't need to solve your optimization problem again. All you need to do is draw a ray line. This is supposed to be a straight line. Draw a ray line connecting the origin at that point. Then this point where for this isoquant curve, or for that output level, then this will also be the cost minimization point. So that means the solution to the cost minimization problem doesn't change. And if you find one least cost combination for a particular output level, then you find the expansion path, because the expansion path for Cobb-Douglas function, as you can probably think, is a straight line. So this is the expansion path for the example that we use for the Cobb-Douglas function. And if we do solve this combination problem for different output levels, then we connect all those points. Then we can find that that's the expansion path, and the expansion path is a ray line. It's a line from the origin connecting all the least cost combination points. So this is a really important result here, is that the expansion path is a straight line, and this is not generally true for any expansion path. So, for example, here in this graph, we can see that the expansion path is not a straight line. So only when we have this very nice property of homogeneous functions where the RTS is constant, then we have the expansion path is the straight line. So if you don't remember this property, you should go back to lecture 11, slide 15. And I spent some time explaining why RTS is constant along ray line. So I explained that the expansion path for a Cobb-Douglas function should be a straight line, which is a ray line connecting all the least cost combinations, and also that line will go through the origin point, which x1 and x2 both equal to 0. So remember that the least cost optimality condition is the ratio of input price equal to the ratio of the MPPs. So here, let me first explain to you what's in this graph. Here I have the ratio of R1 over R2. Right now is equal to 0.5. And later on, I'm going to change this and show you how does the expansion path change. And here, I also have two other parameters here. One is beta 1 and the other is beta 2. And these are exactly the same parameters that we have just explained in the example. So beta 1 is 1/3 and beta 2 is 2/3. So these two beta values will decide the shape of the isoquant curves. And for different level of output, so each output level is one isoquant curve. For different levels of outputs, we have different isoquant curves. And we know if this beta 1, beta 2 is given, doesn't change, then the RTS doesn't change along each relay. And that's just the property of homogeneous functions we have just explained. And also we know that if R1 over R2 doesn't change, then the slope of the isocost curves or isocost lines doesn't change. However, the expansion path does change if we change any of those parameters. So let me first change this R1 over R2 ratio. So if we increase this R1 over R2 ratio, you can say that the isocost curves, it becomes steep. However, this line connecting all the points of the least cost combination is still a straight line. So even if we change this R1 over R2 ratio, we always get a straight line expansion path. That's the property of Cobb-Douglas function. So if we reduce the R1 over R2 ratio, it's the same. The curve, the isocost line becomes flatter, but the expansion path is always a straight line. So now let me change the beta values. And again, each of the beta is the elasticity of production for the Cobb-Douglas function. So if I change this beta 2 value, you can see that the shape of the Cobb-Douglas function of the isoquant curve of Cobb-Douglas function change. So if that change, that means the optimal input combinations to minimize cost also change. So again, here is just to show you that if you have a Cobb-Douglas function, then your cost minimization problem is easier, and it's even easier to find out the expansion path. So I will upload this to eClass, and you can actually use this GeoGebra activity if in the future there's an assignment question, I give you different beta values, different beta 1, beta 2 values, or the R1 over R2 is given, then you can just calculate the R1 to R2 ratio here and change that to whatever the number you need, and also change this beta 1, beta 2 value. Then you can get your expansion path. You can also get the cost minimization point. So this, I hope if you're not understanding why this expansion path should be a straight line, then play with this a little bit. I hope that will help your understanding. That's all I want to show you for the cost minimization problem, or you can say the least cost combination of inputs. And here I actually want to show you duality relationship between cost minimization and constrained output maximization. So what do I mean by duality here? So that means here, this problem is what I have shown you. It's the cost minimization, which means that you minimize your cost of producing a given level of output. So you need to be very careful here is for each given level of output. That's what output minimization means. And if you solve that problem, and you get your solution, which is the input combination. So you will get X1 and X2 in terms of your input price and your two input prices and your production function parameters. And however, if you maximize your output, so here your Y or your output level is your objective, then you're maximizing your output subject to factor cost constraint. And what does that mean? That means your cost is your input price times the quantity of that one input, and then plus the input price times the other input. And you can also plus the fixed cost if there's any. So if you solve this problem, this output maximization problem, then you will get exactly the same answer as if you're solving this cost minimization problem. So that is the duality relationship here. So let's actually find out why the solutions are the same. First, let me formulate this output maximization problem. Sorry, there's a typo here. It should be a output maximization instead of minimization here. So if you formulate the problem here, it should be a max. Remember, in cost minimization problem, it's a min there, MIN, and for maximization problem, then it's your max. So you're maximizing your output level. Your output level is Y, and this because of your production technology or your production function, then Y can be written as a function of X1 and X2. And the choice variables are X1 and X2. Then the constraint here is that your cost is equal to a predetermined level of cost. So remember, in the cost minimization problem, your problem is you're minimizing your cost. Your cost is here. And your constraint is that your output is equal to a predetermined level of output. So now it changed a little bit. Here, the cost, the level of cost is predetermined. And if you solve this problem, you will get exactly the same answer. We have already shown the solution to that cost minimization problem, and the condition is that your input price ratios should equal to your to the ratio of the MPPs. And now let's actually work on the output maximization problem. So here, let's first write down the Lagrangian function, and I put a subscript Y here to differentiate with the cost minimization problem. So this is the Lagrangian for output maximization problem. And I used a different Lagrangian multiplier. Before I used lambda, now it's mu. And again, this Lagrangian function is just your objective function plus this Lagrangian multiplier times. This is actually your constraint here. So you always put the constant level here, and then minus this function of x1 and x2. So this is your Lagrangian function. And once we have the Lagrangian function written down, then the actual process of solving this optimization problem is easier. So again, this should be a maximization, and I will change my slides. So if we have the Lagrangian function formulated, then the optimality conditions is just taking partial derivative of this Lagrangian function with the choice variables here. So those are the 3 optimality conditions, and we can actually simplify this condition here. So this is MPP1 equals mu times R1. And this condition is actually MPP2 equals mu R2. And if we divide both the left-hand side and the right-hand side of one equation by the other, then what we get is MPP1 over MPP2 equals to R1 and R2, and we can cancel that Lagrange multiplier there. And you can find that this is exactly the same optimality condition as the cost minimization problem. So if you're using the same optimality conditions to solve your problem, to solve 2 different problems, then you're gonna get exactly the same answer. There's actually a graphical interpretation for this, and let me show you what does that mean in graph. So the optimality condition for both cost minimization and output maximization problem are the same, which is this R1 over R2 equals to MPP1 over MPP2, the economic trade-off equal to the technical trade-off. And here, let's look at the cost minimization problem first. So in this graph, when you're having a cost minimization problem, you are given output level. So your output level is given, which is this red curve here. So if your output level is given, the isoquant curve is given. So the isoquant curve is this red curve here. Then, in order to solve your cost minimization problem, you're gonna have a bunch of isocost lines, and you have to find out the isocost line that is tangent to your predetermined level y, or to the isoquant of that associated with that predetermined output level. So you find out that this isocost line will be tangent to your predetermined output level, the isoquant of that output level. Then you will be able to find this is your this is the point where your cost will be minimized. So again, you're given an isoquant curve, then you're trying to draw a bunch of different isocost curves, and you want to find the exactly isocost line that will be tangent to your predetermined isoquant curve. However, for the output maximization problem, it's similar. However, this time your cost is given. So if your cost is given, then you have your, remember this in the previous slide we said it's C0. So let's say right now it's given as C1. So this isocost line represents the C1 cost. So then your cost is given. So you are gonna need to maximize your output for this given cost. Then your the output maximization is actually you draw different isoquant curves, and you find out the isoquant curve, which is this curve that is tangent to the predetermined cost. And then that point is your is the point where your output will be maximized. And if you compare these 2 graphs on the left-hand side and on the right-hand side, you'll find out that you'll find exactly the same solution. So the difference is which is predetermined. For cost minimization, its output is predetermined, and then your isoquant curve is given. For output maximization, your ISO cost line is given, then you're changing your ISO quant curves to find out the point. And the solution will be the same. Okay, let's get to the main topic for today, which is profit maximization for two inputs and from the input perspective. And at the end, you will find out there's not much difference between profit maximization for one input and two inputs. There are some, because in the one input case, there's only one mapping between input and output, as we explained before. However, in two inputs case, there's multiple combinations of those two inputs. So let's get started. The profit maximization, first we need to figure out what is the profit. So profit, again, is still your total value of product minus your total factor cost. And remember, from the input perspective, your X is your everything, including your profit, your total value product, your TFC. They're all functions of input. So before, we only have pi as a function of X. Now there's two inputs, so pi is a function of X1 and X2, similar to TVP and TFC. So under the perfect competition in both the product and factor markets or input markets, then the profit can be written as TVP is equal to P times TPP. TPP is just the production function here. And TFC, since we have two inputs, is the cost for the summation of two inputs and also the fixed cost. We find out the profit function when you have two inputs, and let's actually formulate the profit maximization problem. So we are maximizing our profits, and which is equal to the total value product P times Y minus total factor cost subject to a constraint. If our this is actually how should we formulate our profit maximization problem, and if we have profit maximization formulated this way, then we can write out the Lagrangian function for profit maximization problem, and I used a different Lagrange multiplier eta here. And then the next step is you can set those partial derivatives of this Lagrangian equal to 0 and then solve this problem. And this problem can actually be solved a little bit easier, is where we don't need to formulate this Lagrangian function. What we can do is just substitute this production function into our objective function. Then we have the unconstrained optimization problem. So this is actually the profit function that's formulated that way by substitution. And if we have our unconstrained optimization problem, then the optimality condition is, there are three optimality conditions. However, for two input case, I only ask you to use the first order condition, so which is setting the partial derivative of the objective function here, which is profit with respect to the choice variables. So let me first here explain when you have very general TVP and TFC, so we are not assuming perfect competition. Now what's the optimality condition? And in next slide, I'm gonna show you what will the optimality condition change to when we have the perfect competition assumption. So here, first is your profit is equal to TVP minus TFC. So the difference between those two is the profit. And if we take derivative of pi with respect to x1, then we're taking derivative of this with respect to x1 and also TFC with respect to f1. And the partial derivative of TVP with respect to x1 is MVP, so marginal value product. And here is marginal factor cost. So the same for input 2. Then the optimality condition we can find here is that MVP1 equals to MFC1 and MVP2 equals to MFC2. How will you interpret that condition, and what's the economic intuition behind these two conditions? So this is actually means that the return on the last unit of input use, which is MVP. So MVP is the return on the last unit of input use. And I put this quotation mark on last unit is because if you're thinking the partial derivative, which is a calculus concept, then it's not the last unit, it's an infinitely small last unit, or the infinitely small unit. Then the return, which is MVP, is equal to the cost. So the cost of the last unit of input use is your MFC. So the optimality condition, it means return on the last unit of input use and cost of the last unit of input use should be the same. So that's the point where the producer can maximize the profit. And what's the optimality condition look like when we assume there's perfect completion in both factor and output market? So first, the TFC and the TVP can be written, can have an actual function, actual form. So here we are assuming P is a constant, so we can actually written that out. And those R are also constants. It doesn't depend on the quantity of the input used. Then the optimality condition actually translates into these two conditions. So the first one is P times MPP1, which is the MVP1, and MVP1 in the previous slide. Then that equals to R1. R1 is the price, the input price for X1, and that's MFC1. So MFC1. So under perfect completion, then MFC1 just equal to R1. And MVP1 equals to P times MPP1. There are different implications of these two optimality conditions, and let me explain to you why. So the first one is here. So on the left is the are the optimality conditions we have just derived. So we can written it a little bit differently, reorganize the terms. So we put, we put R1 to the left. Then what we get is P times MPP1 over R1 equal to 1. I will explain what that means economically, but here let's first focus on the condition. So this is equal to 1. And we also can do the same thing to the second optimality condition. And again, that term equal to 1. So the two optimality conditions can actually be summarized into this one condition. So PMPP1 over R1 equal to PMPP2 over R2 equal to 1. So how do you interpret those two conditions, or the one condition if we reorganize the terms? So the P times MPP1 is just MVP1 here, the marginal value of product. And from here, we know the marginal value of product for input 1 is equal to the price of input 1. And that means the return on using that input, on using 1 unit of input 1 is equal to the cost of 1 unit 1. So the cost of 1 unit 1 is just equal to the price times the quantity of X1 used. And we see here, we say it's 1 unit. So then the cost will just equal to the price of that unit. So the cost on the last unit of input 1 used equal to the return of the last unit used. That's what we explained before. And here, if we divide the MVP1 by R1, what we get is for each dollar, so on the right-hand side, it becomes 1. So this is the dollar spent on the input 1, the last dollar spent on input 1, and it's not 1 unit of X1, and that actually depends. So, but anyway, here on the right-hand side, this 1 means that that's a dollar spent on each unit. And on the left-hand side, that means that's a return on that $1 of input 1. So this return must equal to the cost. So they on the left-hand side is a return. So the return on the right-hand side is the cost. So again, your marginal return should be equal to your marginal cost. And this should be true for every input use. So here we have 2 input use. However, if our production function, there's n input use, then the optimality condition will just become, let's use I to represent the ith unit. And this is true for all input from 1 to m. So this will be the optimality condition. This is one implication of the optimality condition. There's another explanation of the optimality condition, and this is actually where the condition links cost minimization with profit maximization. So again, on the left is the optimality condition that we derived for profit maximization for 2 inputs. Then if we, again, divide both sides by each other, then we get this condition. And by now, this condition should look very familiar. Why? Is because this is the condition for cost minimization. So if you're given a particular level of output, and remember we use this Y0 to represent when we're giving a particular output. So if you're giving a particular output, then this is a condition where you can minimize your cost, or this is a condition for this cost combination of inputs. And this side, these 2 conditions are the profit maximization condition. So what does this mean? It means that the profit maximization solution lies at some point on the expansion path. And remember, the expansion path is all of the points of cost minimization. If you connect all of the points of cost minimization for all levels of output, then you get your expansion path. And there's actually, let me be a little bit careful here. So pay attention to this arrow here. So this arrow means if you have profit maximization, then you must have cost minimization. However, the arrow doesn't go the other way. That means if you have cost minimization point, that point doesn't necessarily mean it's a profit maximization point. So an explanation here is that, so we have a bunch of isoquant curves, we have a bunch of iso cost lines, and if we connect all those, so each of those points is a cost minimization point. And if we connect that point, that's the expansion path. So this condition means that there's a lot of cost minimization points. And profit maximization could happen at some point. We don't know where. And that's actually, we need to use the information here. And however, here, what I want to emphasize is that profit maximization implies. So this is actually mathematically, this means implies. So profit maximization implies cost minimization. However, cost minimization doesn't imply profit maximization. Cost minimization for all levels of Y, for different levels of Y, you could have a lot of cost minimization points. So you actually have a cost minimization point for each level of Y. However, which level of output should be produced to maximize profit, we actually need more information. So here, I'm again using the Cobb-Douglas function, the expansion paths for the Cobb-Douglas function. However, remember, if it's not homogeneous function, then your expansion paths could be different. It could be in other shapes. So here, those are all cost minimization points, and you have to decide which point is profit maximizing. So as I mentioned, that point, so some point and which point, that actually depends on the information here. So this output price. So here, when we derive the cost minimization condition from the profit maximization condition, we lose this P. So that information was gone. However, that's exactly the information that's deciding which point is the profit maximizing point. So if we use this output price information, then the profit maximization means that if your output price is equal to the ratio of input price to your MPP, then you're at that particular point along the expansion path that will maximize profit. So if this is when we have two inputs. If we have multiple inputs, then we can, the condition will be the same, is where if you write your conditions here a little bit differently, we can also write this as MPPI equal to RI over output price. So if we only have two inputs, then our condition is, is MPP1 and MPP2 equals to R2 over P. So these two conditions is actually very similar to a condition we mentioned for profit maximization when there's only one input. So only one input, the optimality condition can be written as MPP equals to R over P. So I remember I actually showed you a graph of TPP, and from the shape of TPP, you can actually get MPP, and MPP, you can compare the price ratio with the MPP, then you can find the point to maximize profit. So again, here in two input case, it's very similar. It's also the MPP is equal to the price ratio. Let's actually do an example here to explain what we have just shown, how to maximize profit. And again, here I will use the same example, the crop yield example that we have been using for two input case. So again, this is the production function, and this is a quadratic production function. We have two inputs. One is nitrogen, the other is potash. And previously, we haven't do profit maximization. We don't have this information given. And based on the production function, we can decide what's the maximum yield that this production technology can achieve. And if we're given information about the output price and the input prices, then we can actually find the input yield levels that will lead to maximize profit. So assume the output price is equal to 8, and the input price for nitrogen is 1, and the input price for potash is 0.75. Then how will we find, or how can we find the maximizing profit? So we should use the optimality condition here. And remember, for two input use, there's two optimality conditions, which is the MVP for a particular input should be equal to the MFC for that input. And let's actually do this step by step. So we have two conditions, MVP1 equals to MFC1, MVP2 equals to MFC2. And to use this condition, we actually need to find out what are the MVPs and what are the MFCs. MFCs in the perfect competition assumption, or under the assumption, then the MFCs are just equal to the input price. So that's really easy to find. Then we need to find the MVPs. So MVPs under perfect completion is equal to P times MPP. And so the first step is actually to find out what's the MPPs. So here you need to be a little bit careful, and I do apologize for the notation here. So capital P means it's for input potash, and smaller p is for output price. Okay, so the MPP here, those two MPPs, we actually have shown how to derive those in previous lecture. It's just taking derivative of your TPP, partial derivative with respect to N, to your, and this one is with respect to P. So you got your MPP times the output price. This is output price, smaller p. And then these two equations are your MVP equations. So the next step will be to equating the MPPs to MFCs. And if we set those two equal to each other, then this is the two equations that we are gonna need to use to solve for two unknowns. And I have the detailed steps to solve those two input use levels in the next slide, but I'm not gonna go over them here. So if you're having difficulty solving those two levels, then maybe you should pay attention. You should go through this process here listed in this slide. However, if you go over all of those steps, then you should be able to get those two optimal levels. So one is nitrogen, the other is potash. And again, once you solved your input use levels from the optimality conditions, then you put a star there to indicate that that's the optimal input use. So we actually find out the input use levels that will maximize our profit, and we should actually go back to plug our input use levels to both the production function and the profit functions to find out the output level that will maximize profit and what is actually the maximum profit that we can get. So you put your optimal N and optimal P into your production function, then you can get this optimal Y. Sorry, this is not an optimal Y. This is the output that will lead to maximized profit, and you can get your maximized profit, and which is equal to this number here.